It's a bunch of theorists trying to run that.
Yep.
Okay, I think we're good.
Okay, great. So the first thing is, does anybody have any questions from last time? So last lecture was experiment. Everybody understands everything about experiment. Okay. So did anybody try the homework? Does anybody remember that I mentioned something as a homework problem? Yeah, I just mentioned briefly when we were discussing the tau that you could estimate for yourself the branching ratio for taus to go to leptons, either E or mu. And there was a big table, and the branching fractions were roughly 17%, I think. Anyway, there's an easy way to understand why taus go mostly to hadrons. This is a graph of the tau decaying to a tau neutrino and an electron and its antineutrino. And for the branching ratio, we want to take that rate or partial width and divide it by the total decay width of the tau. The total decay width of the tau includes the two leptonic decays. One would be to the muons, but it's the E and mu are the same because me and mu are both much less than m tau. And then there's a hadronic decay of the tau plus a tau neutrino. And that can be estimated by going to UD bar. Why did I only put in UD bar here? Why didn't I put in any other quarks? Anybody know? That's right. At least the charm quark, well, the charm quark mass is not really the relevant thing, but anytime you have a charm quark, it has a mass that is greater than or equal to the mass of the lightest charm state, and that's the D meson. And MD is about 1.8 GeV, and that's greater than m tau, which is just slightly less, actually. But anyway, so you can't put charm here. You could try to put an S quark or S bar instead of a D bar. Why didn't I bother with that? Yeah, exactly. So that would, make like a 4% change. If you look in the table, there are some kaons in the table, but they're very small. So you can basically approximate it by UD bar. And these graphs look exactly like these graphs, except for one difference. What's the difference? Yep. Color, exactly. So you have to sum over the fundamental representation of SU3. You get a factor of NC equals 3. So basically, your numerator is 1, and the denominator is 2 plus 3, roughly. So this is 20%. The actual answer is a little smaller, around 16%. And that's because this has QCD corrections to it. And those make the hadronic width go up some. In fact, that's one of the ways of measuring the strong coupling constant is by using the tau branching fraction. It's a little bit tricky because at these low scales, alpha S is quite big and the perturbative series isn't so well behaved, but it gives a pretty decent measurement of the strong coupling by including the higher order alpha S terms. Anyway, that was just a little thing about the to understand qualitatively a little the properties of the tau. Now I wanted to go back and do a few things in this lecture. We'll see how far we get. But I kind of wanted to give you an overview of the QCD improved parton model, which is the basis for 95% of the measurements done at the LHC. And then I will spend a little time on the blackboard discussing the parton model in deep inelastic scattering, partly because I'm at SLAC, and that's where deep inelastic scattering was first performed, and partly because it's simpler than doing it in proton-proton collisions. And then we'll come back and to the LHC again and discuss a few more issues like infrared divergences and IR safety, parton distributions and their evolution, and what the basic structure of higher order QCD calculations are in the sense of which amplitudes do you need for which orders and so on. Also maybe, as time permits today, maybe tomorrow, talk about just various levels of approximation and what the rough status of computations at different orders is. So this is maybe a theorist's view of a LHC collision. We already saw examples of experimentalist views in terms of tracks and calorimetry and stuff. But this is from Frank Krauss, who's a author of one of the Monte Carlo programs used to describe the sort of global event structure of LHC collisions. And it shows you that it's a big mess. So you have these composite particles, protons, in green there, that are coming in from the left and the right. And inside them are, we think of them as sort of searchlight beams of almost parallel quarks and gluons, the quarks in the solid lines, the gluons in the curly lines. And every now and then when these protons are overlapping, there may be a parton inside that gets close enough to another parton to undergo what we call the hard collision. And we can describe that using something called a short distance cross-section. But there are all sorts of other things that happen that make it more challenging to get back to the short distance physics, which we can describe in perturbative QCD. And those include things that happen before the collision, where the parton that collided might have, before it collided, branched or split from some other parton. Like here, the gluon that collided here might have originally been described as a quark inside the proton, but it underwent a collinear branching where this quark split into a gluon and another quark. Now, as we heard from Jake yesterday, in real momenta, you can't have a on-shell three-point function, but this thing could be just very slightly off-shell, and then the process can factorize, where this is essentially a three-point massless vertex. But there can be additional branchings that happen as well, and you can branch in the final state. This is called initial state branching, and this is final state branching. Here, you might have produced in the gluon collision a Higgs boson. That's a color singlet, so that can fly for a while, but if the Higgs decays to quarks, then those quarks also have a chance to do final state branching. And these branchings are typically quite collinear, although they can also be wide-angle soft. And the collinear nature is what gives us these collimated clusters of hadrons at the end. But before you can produce hadrons, you need to sort of think about how this shower evolves. And Monte Carlos will do this for you based on a certain approximation to QCD. And then with these large number of partons, they all have color under QCD, and you need to find a way of sort of hooking up the color in order to make color singlets and some model for how you produce hadrons. And this part is pretty model dependent, and there are different kinds of models, string models and cluster models. But they also probabilistically, after implementing this shower, the so-called parton shower, based on perturbative QCD, resummed in a certain way, then you apply one of these models to attach, to turn the colored particles into color singlet particles and decay them into hadrons. And so that's a sort of rough sketch of a basic Monte Carlo simulation. And a lot of the challenges are to, well, improve some of these models by studying all sorts of different kinds of data from the experiment, and also improve the accuracy of how this parton shower is coupled in or matched to higher order perturbative calculations when they're available. But these are the sort of the predictions based on models like this are what the experimentalists usually use day to day to understand what is going on when they study a particular process. Now, the reason why we can make any progress at all is because at least that short distance part is done in a region where the strong coupling is small. And this is all thanks to asymptotic freedom. As you know from your QFT courses, in QED, the electrons screen the electric charge. This vacuum polarization diagram has an ultraviolet divergence. When you renormalize it, you have to introduce a renormalization point or scale. And when you're at scales much less than the electron Compton wavelength, there's a logarithmic running, and the leading order running behaves like this, so that alpha gets stronger as mu squared gets larger, the momentum scale mu. Whereas in the Yang-Mills case, the quark has exactly the same properties as this up to some color factor, and the gluons have the opposite sign, and therefore you get a plus here with the famous formula for the first coefficient of the beta function involving 11nc and 2nf. So I'm hoping you've all seen that before. And basically the coupling runs logarithmically to 0 as mu goes to infinity. And so that's the calculational story as it was 45 years ago or something. But nowadays, we know the running much more accurately. The 3-loop coefficient was computed in 1997, and beta 4 is too long to fit on this slide. But it was computed just a couple years ago. And so we know this evolution extremely accurately now, given a measurement at any point. There have actually been lots of measurements of alpha S done over many years. This slide is already almost a decade old, but it shows a lot of very accurate measurements. There are measurements at the z-pole from jet rates in E plus E minus colliders. I mentioned that tau decays. That was calculated back then even at N3LO in perturbation theory, and it gives a pretty decent error bar. The error bars are worth more here because when you run the strong coupling down, it focuses. That is a difference between two values of alpha S here. When you run the evolution equation, it becomes smaller up here. This is the reference point that everybody evaluates alpha S at, the z-pole, 91 GeV. And this is the world average as of 2011. It hasn't changed much for a while. But there are lots of other ways you can measure alpha S as well. So this is the parton model as we use it at the LHC. And it's based on the notion, again, that there are hard partons inside the proton, quarks, antiquarks, and gluons. And they each have their own distribution function, different distribution functions for different flavors of quarks as well. And so you will sample with a probability depending on the longitudinal momentum x1, say coming in here, going into this collision, and x2 coming from the second proton. And these PDFs will also depend on mu-f and on a sort of a scale for what you call the factorization scale. And then you need to compute a probability of these hard partons interacting, and that's called the short distance cross-section. And it is a function only of the momenta of this smaller piece of the collision. The overall collision has center of mass energy squared s, but because these momenta have a smaller fraction, x1 and x2, the center of mass collision energy for the short distance cross-section, sometimes called s hat, is really s times x1, x2. And this will also depend, and this has a perturbative expansion, depends on alpha s. It also depends on the scale that you renormalize alpha s at, and the factorization scale. This is a very simple example, which is called Z production, or sometimes more generally Drell-Yan production, because it can produce a lepton pair. But of course, this whole picture can be applied to many other processes, but not everything is calculable perturbatively in this way. So that's what I said, that FA is the probability of finding parton A in proton 1 with the fraction x1 of its momentum. And then there are these arbitrary factorization and renormalization scales. Now, this is based on a lot of, was originally based on some empirical pictures, but they were developed first in deep inelastic scattering. So I want to just discuss deep inelastic scattering a little bit. And so deep inelastic scattering is electron or lepton-proton collisions. So we could have a lepton being either electron or a muon. Electrons were used at SLAC in the 1960s, and muons were used at Fermilab and CERN later on and gave higher energy. And then there was a collider, Hera, they used at DESI. They used electrons and positrons, and it was colliding beams, so it got to much higher energies. And so we're going to do LP scattering. So we have a lepton that comes in here and goes out here with momentum L1 and L2. And it interacts through a virtual photon with something in the proton. So Q is L1 minus L2. And here's the proton with momentum P. And this system here is the set of all the hadrons that are produced. There may be lots of gluons flying around here as well. So we could call this system X. And the momentum of X is Q plus P. So it's traditional to, now how many different kinematic variables does this depend on? There's some Lorentz invariant dot products like L1.P. There's also L2.P, but we could trade that for Q.P. And there's also Q squared. So there's basically 3 different variables. Also, P squared is the momentum of the proton, is the mass of the proton squared. And we're going to work in a limit where that's small, generally. So it's convenient to trade these variables for, well, Q squared we more or less leave the same, except that we recognize that it's less than 0 and introduce a positive quantity, capital Q squared. And then the variable X is minus Q squared over 2 P dot Q, which is also Q squared over 2M E minus E prime, where these are the energies of the leptons in the lab frame. In the frame of the proton. Rest frame of the proton. And also Y is Q dot P over L1 dot P. So if we did elastic scattering, that would mean that the final state would just be this lepton plus a proton, and that would correspond to px squared equals m squared. But that's also q plus p squared, which is q squared plus 2 p dot q plus m squared. So if we subtract m squared from both sides, then that says that minus q squared over, that 2 p dot q is minus q squared, or x equals 1. So the elastic limit is x equals 1. So deep inelastic scattering is to take q squared very large, like much bigger than m squared, but keep x finite, less than 1. And that requires that the px squared is starting to get very large too, very large invariant mass final states. Now, another thing you can do is imagine that the actual collision involved a particle that had a momentum c times the momentum of the proton, and it collided with this virtual photon and produced an object that had that was also massless. In that case, you would get that q plus cp squared is equal to 0, which is q squared plus 2c p dot q. And if you solve this equation, you see that c is equal to minus q squared over 2p dot q, which is what we defined x to be. So that was the reason we defined this combination to be x, because in the case that the virtual photon strikes a massless parton inside the proton, and that's all that happens, that there are no other interactions, then the kinematic relation tells us that, that x is just the fraction of momentum carried by that parton that was hit. So x is a key variable in describing the structure of the proton. Any questions about that? So I just did a little kinematic exercise that says, suppose that the virtual photon collides with an approximately free massless particle inside the proton. But that free particle doesn't carry the full momentum of the proton. It's traveling parallel to it, but it has only a smaller fraction, which I'll label xi. And suppose further that in that collision nothing else happens, it doesn't radiate anything else, it just comes out, then momentum conservation tells me that the sum of this momentum and this momentum squared should be 0, right? So that's what I used here. And that condition, expanding this out, also I'm neglecting the proton mass here, so p squared is 0, so I don't have the third term. Then I take this and I solve it for xi, move the q squared to the other side and divide by 2p dot q, and I see that xi has the exact same formula as x. Okay, so that tells us that x can be interpreted to first order in QCD as a distribution function of hard stuff inside the proton, up to some factors of electric charge and stuff we'll get to later. Any other questions? Okay, so now, as you know, experimentalists don't measure amplitudes. They measure cross-sections or differential cross-sections, which are basically amplitudes squared. So let's redraw this graph again, but kind of square it. So there's a mu index on here and a nu index on here. And this amplitude factorizes more or less into a product of two pieces. So this is called the leptonic tensor. And this is the hadronic tensor corresponding to the lower part. And the leptonic tensor is proportional to a Dirac trace of L1 slash gamma mu, L2 slash gamma nu. That's just from writing the amplitude that you saw in, I think, Eric and Alex's maybe vertex, you know, the gamma mu here sandwiched between a spinner, which is going to get multiplied by a conjugate spinner, and then we put in the positive energy projectors, which for massless particles, we're neglecting the lepton mass here, is just the slashed momentum of that particle L1, and then on the other side, L2. Everybody familiar with that? The just basic Casimir trick for squaring up a typical fermion string. So that has a L1 mu when you evaluate this trace. It's proportional some number, like 4 or something, which I'm not keeping track of. But anyway, the leptonic tensor has a very definite form, whereas the hadronic tensor, in general, before we apply factorization and sort of perturbative QCD, it has a, we can write it as a more generic form where since the bottom part only really depends on Q and P, and also it should be transverse, it has to be expressed in terms of some scalar functions called form factors. And then there are various tensors that can carry the mu and nu indices. That can depend on P and Q. So there should also be some Q terms that follow from current conservation. There's some transversality. I omit them because they don't matter when you contract with the leptonic tensor, because the leptonic tensor has the property, as does the hadronic one, that Q mu L mu is 0. Current conservation. So you're going to get two different results for the kinematic dependence when you contract the leptonic tensor with G mu nu. That's going to give a L1 dot L2 factor. Whereas over here, you're going to get a L1 dot P, L2 dot P. Now it turns out that W1 scales properly And that means it gets renamed F1, which can depend on x and q squared. But it's more convenient to define another function, something like now, when you go through the business of contracting with the oh, I should also say this one's 0. The only reason I put it in, it's 0 because this is this is symmetric in mu and nu. But in some cases, when you have a polarized electron, then you would get a different, you would get the polarization coming into the leptonic tensor, and then you could get contributions from W3. Also, if you use weak interactions, you can get contributions like this too. But we don't need it here. So we just have two structure functions, F1 and F2, deep inelastic structure functions. Now, when you take into account you get this factor of L1.P and L2.P and L1.L2, you get a formula, and there's some Jacobian for changing to these variables x, y, and q squared, that the differential cross-section in these variables is it has a 1 over q to the 4th from the photon propagator, and then it has a y squared x f1 plus 1 minus y f2, which can also be rewritten as so this looks a lot more complicated than the first form, but it's useful in view of what comes later, or comes soon. So this is just some algebra I didn't do for you, but if you pay attention to some Jacobians and stuff, at least you can see that this 1 minus y involves L2.P over L1.P. And that comes from the fact that there was a L2.P in here, whereas this one has like a 1 over, it differs from it by a relative factor of L1.P, L2.P. And then you can check the algebra that this is the same as this. But why did I write it that way? Well, we want to go back to this parton model. We want to go back to this idea that we have an object with momentum Cp, which is a spin-a-half particle, and evaluate the lepton gamma star quark amplitude. And so that matrix element squared now, by Friday, you will have evaluated all tree amplitudes and all gauge theories in your Mathematica notebook. But just trust me for now. This has a factor of the quark charge squared times e to the 4th for the overall. This is the quark charge in units of e. And then we also get e. And then this squared matrix element is very similar to the ones for e plus e minus to QQ bar, or e plus e minus to mu pairs, or Drell-Yan. They're all the same up to crossing, that is the relabeling s hat, u hat, and t hat. And t hat is the momentum in the t channel. For this, that was just the from the momentum vector from the virtual photon, that is just minus q squared. And S hat is L1 plus xp squared, which is where you only get a contribution from the cross term, 2xc L1 dot p. And actually, let me take it to be x now. So the momentum coming in here is xp. And using the relations for x can be rewritten as q squared L1 dot p over p dot q. So then S hat, looking up there, is something like q squared over y. And U hat is minus S hat minus T hat. And that works out to be minus S hat 1 minus y. So when you take this matrix element for this short distance cross section and plug in these values, and you get something like 4 pi alpha squared. I'm not paying any attention to overall factors that are constants, really. But it basically looks like this. There's also some Jacobian factor to go from the squared matrix element to here. And at the end of the day, you get d3 sigma dx dy dq squared is so I'm taking into account that kinematic relation. I'm being a little sloppy about whether this was really x or xc because they have to be equal to each other. But if it were xc, then I should put in this delta function. And you notice that the y dependence here exactly matches the first term. And it doesn't match the second term. So what that tells us is that in LO leading order QCD, where the only electrically charged constituents of the parton are quarks, that is spin a half electrically charged objects, we should have F2 equals 2 XF1. So this was an important measurement early on to verify this Callan-Gross relation. And then from the non-zero term, we can compute what the distribution is in terms of the quark distribution. So basically, if we take this delta function and we then assume that there's a distribution probability we call Q of xc for the momentum in the interval of xc to xc plus dxc, then we find that F2 equals 2xF1 is equal to just the sum over the different quarks, EQ squared times Q of x. So this is the lowest order relation between the structure functions in deep inelastic scattering and the underlying parton distributions. Now, there's another way of analyzing the system, but are there any questions about this first? Yep.
This assumes that you can resolve the constituents in the proton.
Yeah, so that's sort of leading into the next thing. In other words, what we basically assumed was that this virtual photon has a high enough transverse momentum which sort of focuses the time in which it interacts with the quark to such a short time and distance that there are no other partons in the vicinity that it can interact with. And also that the coupling becomes small at those distance scales so that the probability of radiating some additional particle that will change the kinematics is small. And one way to try to analyze that is by thinking about products of operators. So this is a operator, the electromagnetic current at a given point. And here's another current at a separate point in the cross-section. And the large momentum transfer allows you to, that configuration is dominated when those two operators are close to each other. So you can apply an operator product expansion and try to identify the partons corresponding to operators in that expansion. Julian?
So a question,
Yeah.
for this last one. So in the previous expression, you had an X in there, right?
Yeah.
And you match it to the on the left-hand side, which also has an X, but then in your relation.
Maybe I missed a factor of X too. I think I should not have had that in there. Is that the right way? Yeah, I think it's probably like that. I think I just put that in by mistake when I was looking at the wrong F. Any other questions? So let's switch boards again. So that the hadronic tensor W nu that only depends on P and Q, which translated into only depending on X and Q squared, basically. It's, I'm just going to put a lot of tildes in here. It's a sum over the hadronic states X that satisfy momentum conservation of some matrix element of the electromagnetic current to make X, and then the conjugate amplitude. So And there's the electromagnetic current. And this is also basically the imaginary part of a Fourier transform with momentum q. And this is just the position x, not the previous x, which is, the previous x is often called xbj, the momentum fraction, but this is just a position variable. So you want to take the transform of the product of two of these currents here, and this matrix element in the proton. So the notion is that because Q is very large, the relevant configurations have X very close to 0. These two operators should be inserted at almost the same point. And then you can expand this in an operator product expansion, which has over a generic set of operators near the origin, which have some expansion coefficients that depend on Q. Now, in general, if you have a high dimension operator, you will need a lot of powers of Q squared in the denominator by dimensional analysis, because this stuff here doesn't really know about the momentum of P. It's just dependent on Q. And so if there should be a dimensionful dependence, which is 2 minus d, when this operator has dimension d. But there may be some other factors of Q that can come from the structure of these OPE coefficients. And if the operator has high spin, so let's write an operator with dimension d and spin n that has Lorentz indices mu1 to mu n, which are all symmetrized, then it's going to have a corresponding OPE coefficient, which will have a lot of free indices on it. And since those really depend on Q, at least the leading terms, all of these indices should be soaked up by momentum Q. We can also make them dimensionless by dividing each one by 1 power of Q, so that we leave all the other dimensionality in this Q to the 2 minus d. So what we find when we take matrix elements of this operator is that we get, now in this state with momentum P, we get a lot of P's to the mu n's. And those will contract up with these Q's. And then we can use the fact that P dot Q scales like Q squared because X, which is Q squared over 2 P dot Q, is of order 1. So then we can get additional powers of Q in the numerator coming from these contractions. So the final contribution to W of one of these operators goes like P dot Q to the n over Q, Q to the 2 minus d, which goes, and this gives a Q squared, so it goes like Q to the 2 minus d plus n, which is often rewritten as Q to the 2 minus t, where t is called the twist, which is the dimension d minus the spin n. So the most important operators in deep inelastic scattering, which correspond to only hitting one quark at a time, are called leading twist. And for quarks, they include Q bar, with some gamma matrix. And if I just put a quark here, this would be d equals 3. But this gamma mu index would make it spin 1. And so the twist would be 2. So the leading twist is 2. But you can also insert additional covariant derivatives here, d mu 2, d mu 3, etc., up to d mu n. So there's an infinite sequence of these leading twist operators. And there's a similar set for gluons, which are something like g mu 1 alpha, d mu 2. And basically, there's a connection, which I'm not really going to, I'll just state it here, that the parton distributions we were discussing earlier, like Q of x, they are related to matrix elements of these operators inside the proton through a Mellin transform. So the variable x naturally runs from 0 to 1, since it's the probability of finding a momentum with that fraction. And we can Mellin transform it by multiplying it by x to the n minus 1 and raising it to the n minus 1 power. And that will be the quark operator, the leading twist series of quark operators. Put an n on that. And similarly for g of x with OG. There are many other operators that have higher twist. For example, you could have Q bar, some gluon field Q. And you would, the reason why this stays leading twist is because the covariant derivative gives you 1 unit of spin for each dimension. And so you don't lose anything when you put in this covariant derivative. But if you put in a gluon field, that has dimension 2 because it's a derivative of a mu, but it only generates 1 unit of spin because of the anti-symmetry between the two fields. So that's higher twist, and physically it would correspond to a contribution where, say, a quark, it involves a combination of a quark and a nearby gluon that it's interacting with during the time of the collision. So those contributions should all be suppressed roughly like powers of q squared in deep inelastic scattering. So I think now I'll go back to the slides, unless there are any questions about that, at least for a little while. Oops.
Sorry, if you compare with the standard light cone OPE, like the stress tensor is dominating the OPE, so how would you compare with this OPE that is dominating the deep inelastic scattering?
Well, I think this is an OPE along the light cone.
Yeah.
And that's kind of, there are other OPEs where there isn't like a large light-like variable where you get sort of a finite set of local operators. But, so I'm not quite sure about the stress tensor one. I mean, like for example, when you do weak decays of hadrons, there you can do an OPE expansion, but you only have a small number of operators contributing at leading order in the light hadron mass divided by the W mass. In this case, you get an infinite set of operators because there's this large momentum in the game that things are moving along a light cone. Anything else? So let's see. Actually, we've been going for an hour. Probably it's a good time to take a break for a few minutes. And then we'll come back and start this later. How's that sound?